Exercise 236 is about localized and delocalized lone pairs. Localized lone pairs are lone pairs that are stuck in one location. And delocalized lone pairs are lone pairs that are spread out over more than one atomic location. So they're on more than one atom. Now, the rule you can use, the shorthand rule that you can generally use on a test, is that an atom is localized if a lone pair is localized if the lone pair is involved in no resonance. If it's part of one of the resonance patterns, then it's going to be spread out over atoms. That's what resonance does. It spreads electrons and their charge out. And so if a lone pair is involved in one of the resonance patterns, then it's going to be spread out. It'll be delocalized. So that's a sort of shorthand that you could use for these problems. The exercises, though, are asking about a little more information. They say, indicate whether each lone pair is localized or delocalized. So that means, does it have resonance, or is it missing resonance, or does it not have any resonance involved with it? And then it asks you to use that information to determine the hybridization state, so sp3, sp2, sp, and the geometry for the atom that exhibits the lone pair. So this is really asking for three things. 1, localized or delocalized. 2, hybridization state. And 3, geometry. And so to really understand this and to see how 2 and 3 fit together with the resonance, we want to go back and explain the reason behind these 5 resonance patterns. Why are there 5 patterns? Why not 12 resonance patterns or just 2 resonance patterns? Where did these patterns come from? And for that, we want to explain, we're going to go back to how bonds are formed. Remember, there are 2 types of bonds. There's a sigma bond, and you form a sigma bond when 2 orbitals overlap, and the overlap isn't interrupted at all. On the other hand, if you have 2 orbitals like P orbitals that overlap, so they do overlap, but there's an area in the middle where the overlap is interrupted. This purple area here, there's an interruption in the overlap. That's a weaker bond called a pi bond. And it's weaker because the overlap is interrupted there. So these are the 2 types of bonds you can have. And in general, pi bonds will be made in organic chemistry. They'll be made from parallel p orbitals. Parallel p orbitals. Remember, each carbon atom has 1 s orbital and 3 p orbitals that are all perpendicular to each other. 1 in the y direction, 1 in the x direction, and 1 in the z direction, coming out and going into the page. So 3 p orbitals. In order for 2 atoms to have a pi bond, so an atom here and an atom here, both of the atoms need a p orbital that's parallel. One p orbital can't be y and the other x. In that case, they don't overlap to form this pi bond. They both have to be parallel. And then they'll overlap at the nodes, and they'll have that place where they don't overlap in the middle, as is clearly drawn there. Okay, well, what all of these resonance patterns have in common has to do with the pi bonds. We said you get a pi bond if 2 atoms have parallel p orbitals, and so they overlap a little bit. So here's an atom, here's an atom. But what happens if you have another atom over here that also has a parallel p orbital? Well, then you form another pi bond so that the electrons that were just between these orbitals are now spreading out over more orbitals. And if you have another atom that has a parallel p orbital, then those overlap and the electrons can spread out over even more atoms. So that's what's behind all of these resonance patterns, parallel p orbitals. For example, in this ring, in order for you to have this pi bond here, that ring, the carbons have to have a p orbital here and a parallel one right next to it, and they overlap to form the pi bond. In order for you to for the molecule to have a pi bond there, you have to p orbital here and a p orbital here, and they overlap. In order for the molecule to have a pi bond there, you need a p orbital on each one that is parallel. But notice, all of these p orbitals are parallel and right next to each other. So there's no reason for the electrons just to stay between these two orbitals. They can spread out between those. And as they move between those, they can spread out to the next one and spread out all the way around the molecule, because all of the p orbitals are parallel and next to each other. That's what allows the electrons to spread out, and that's what makes the bonds intermediate between single and double bonds. In this fourth pattern, you had a p orbital here and a p orbital on this atom, and that's what allowed those electrons to spread out. Here, you have one of these lone pairs in a p orbital, and this positive charge is an empty p orbital, and that's what allowed the electrons to spread out. To have this pi bond, you'd have these two parallel p orbitals, and this positive charge is an empty p orbital, so the electrons can spread out over all three atoms. And with the allylic lone pair, to have this pi bond, you'd need parallel p orbitals on these two carbons, and then one of these lone pairs can exist in a p orbital. So all three of these are parallel, and the pi bond spreads out over more atoms. So these resonance patterns are the different ways where you could have parallel p orbitals in succession. So, in other words, any time you have resonance, the atom that has the resonance has a p orbital. That's the only reason why it has the resonance in the first place. If it's using one of its p orbitals for resonance, then it can only mix the s orbital with two other p orbitals, and the molecule will be sp2 hybridized. So you'd put 3 orbitals in, and you'd get 3 orbitals out, 3 Frankenstein orbitals out, that look a little bit like that. The fat lobe is the lobe where the s orbital added, and they still have the sort of p shape. And when those repel each other, they push each other at the corners of a triangle. And that triangle is flat, so it's trigonal planar. The molecule will be, around that atom will be trigonal planar. Now the p orbital on top of that would be sort of going in and out of the plane perpendicular to those. So, in other words, if a lone pair is involved in resonance, then the lone pair must be in a p orbital. That's what's letting it spread out. And if the lone pair is in a p orbital, then the atom it's on must be sp2 hybridized and trigonal planar. All right, let's apply that concept here. First, let's draw in the lone pairs. This nitrogen has one lone pair, this nitrogen has one lone pair. First things first, let's do the first step for each of these, localized or delocalized. So let me actually keep the tab below them. Okay, these lone pairs are not involved in any resonance patterns. If you go through all 5 of them, the 2 that have lone pairs in them are the first one, allylic lone pairs, but that's not allylic because the atom one atom away from it is not involved in a double bond, so you don't have that one. And then a lone pair next to a positive charge, but there's no positive charge there. So this is involved in no resonance patterns, and so it's localized. That lone pair is stuck just on that one atomic location. These lone pairs here are allylic. They're one atom away from an atom in a double bond. So those are going to spread out through resonance so that those lone pairs don't just exist on this one atomic location, they move over multiple atomic locations, so they're delocalized. Okay, so that's the first thing. Second thing, what's the hybridization? Well, if this atom is, if these electrons are delocalized, they must exist in a p orbital that's parallel with these. And so, if it has a p orbital, only two other p orbitals can be mixed with the s to give sp2 hybridized. You only have the two other p orbitals to mix with the s orbital. And if it's sp2 hybridized, as we saw, it's trigonal planar. That's the shape around that. Now for this other one, those are localized. So that means it's not using any of its p orbitals. So you can mix all three p orbitals together with the s and get sp3. Mix one s with three p's. Now the shape of this, if you look at that nitrogen has a lone pair, two hydrogens, that's what this H2 is telling you, and then a bond to that carbon there. In other words, it has three bonds and one lone pair, so it's trigonal pyramidal. So if it is not, so in any localized, on an atom that has a localized lone pair, you find the shape in the exact way that we did for chapter 1, using a combination of bonds and lone pairs. All right, let's go through the same pattern for B. So we're looking for three things. Now first, let's draw the lone pairs in. This oxygen has 2, this oxygen has 2, this nitrogen has 1. That gives them, all those atoms, 8 valence electrons. Okay, I'll do these in different colors. This nitrogen here, first, let's go through that one. Is that involved in any resonance patterns, this lone pair? It is. It's one atom away from an atom in a double bond. So it is an allylic lone pair, and it's going to spread out. Right? We saw the pattern for that as it goes here, and it kicks those electrons up. So those electrons move or spread out over multiple atomic locations. So that is delocalized. Delocalized. Now the only way those electrons in that lone pair can be delocalized is if it has a p, if they're in a p orbital that's parallel with p orbitals on those atoms, so that they spread out through the whole thing. Which means this nitrogen is already using one of its p orbitals. So it can only has 2 left to mix with the s, so it's sp2. And any sp2 hybridized atom is trigonal planar. So notice, it looked like this nitrogen is similar to that one, but because this nitrogen has electrons that are involved in resonance, it needs a p orbital that changes its hybridization and its shape from what it is when it doesn't have resonance. Okay. Let's use a different color. This color will be for this oxygen. So first, what's the hybridization, or I'm sorry, these lone pairs. Are these lone pairs involved in any resonance patterns? Those two specific lone pairs. And they're not. Those lone pairs are not allylic. They're on an atom in the double bond. They're not one atom away. And those lone pairs are not next to a positive charge. There's no positive charge on the atom adjacent there. So because there are no resonance patterns for those two lone pairs, those lone pairs are stuck just on that oxygen, and they are localized. So that atom is not a centralized atom, so the shape here we won't have to worry about. For the hybridization, this oxygen does have a pi bond, and so it needs a p orbital for that pi bond, so it only has 2 p orbitals left. It's sp2. And because it's not a central atom, because it's only connected to one other atom, it doesn't have a molecular geometry. Its electrons will point in sp2 orbitals that are trigonal planar, but as a molecule, it doesn't have a geometry. So you could just say not applicable for our class. Okay, let's do this third one, lone pairs there. Are those lone pairs involved in any resonance patterns? They are. Those are allylic. If you go one atom over from those lone pairs, you are in an atom in a double bond. So one of those lone pairs can move. They both can't move. One of them can move over to do the resonance, and it doesn't matter which one. So one of these lone pairs can move. So it will be delocalized because it's associated with a resonance pattern. If it's delocalized, it has to be in a p orbital that's parallel with the p orbitals in this pi bond. Oops. That means that that oxygen is using one of its p orbitals, so it can only mix two other ones with an s orbital. And if it's sp2 hybridized, the shape around it is trigonal planar. Now you might say, wait a second. In the first chapter we learned if you have two lone pairs and two bonds, that shape is bent. But remember, this isn't really a lone pair here. That is delocalized. That's not stuck on that one atom. That's spreading out over here. So you wouldn't have that lone pair there. That lone pair is existing in a p orbital. And so that only leaves three places where you have electrons pushing each other apart, which would give you a trigonal planar shape. Okay, a trigonal planar electron geometry. Okay, let's go to C. And actually, I'll stop there. We'll do C, D, and E, F in separate videos to avoid making the videos too long. Just one last note about 236b. We mentioned how these electrons here would be in a p orbital that's parallel with these two. What about the other electrons, these over here? Well, if the electrons we talked about, if those are in a py orbital, for example, so that they're parallel with the other ones, then these cannot be in another py orbital. There's only one py orbital. So there's no way for the other lone pair to be in a p orbital that's parallel with the p orbitals in the pi bond. And so that one is not involved in resonance. It would be localized. And because it would be localized, it wouldn't spread out, so it wouldn't be quite as stable. The atom we already saw was sp2 hybridized. That's because the other lone pair is in a p orbital. And so you would have an electron geometry that would be trigonal planar. So anytime you see sp2 hybridized, you could just put trigonal planar. That's okay. Just keep in mind what you're getting there is the electron geometry. It's the distance away from all the electrons, whether they're in bonds or lone pairs. It's not necessarily the shape of the molecule. In other words, the shape of just the atoms around each other. So I just wanted to point out that those two lone pairs are in different orbitals. And so one of them is delocalized, and it could be either one you are choosing, But if one of them is delocalized, the other one has to be localized, because there's only one py orbital on that atom.